So, how do I then how to choose probabilities for edges? Well, the intuition comes from our intuition of the cuts that we were talking about, right? So, which edges are important for cuts? In some sense, that's the question. That's the intuition that we should build, right? So, if my original graph, let's say, if I had a graph like this, and then I had all the edges. Let's say I had this like a complete graph, right? So, all n choose 2 edges are there. Maybe I won't draw all edges, but let's say imagine all the edges are there, right? So, now no single edge is so important, right? So, let's say for example, if I am somehow wanting to understand the effect of this edge, let's say this is u, this is v. Now, with respect to cuts, right? So, if this edge is gone, the cut sizes are not going to change so much, right? So, this edge is not kind of critical for any cut. On the other hand, let's say we have another setup where, let's say we have two such complete graphs, right? So, something like this. Yeah, okay, okay, something like this. And now let's say there is this extra edge. Now let's say this is my graph, and I am interested in, how important is uv now. Well, uv is very important because if in the sparser version, if I miss out uv, then my cuts are going to get computed completely differently, right? So, for example, this cut, earlier had one edge going. Now, suddenly the sparser version, if that edge is not there, will have 0 edge going, right? So, there is like an infinite loss that I incur. Whereas, in this particular case, if this uv was not there in the sparse graph, even if I take any cut, this edge will contribute to 1 less, but then, instead of 100, I might have 99. That's still okay, right? So, but then having 1 versus 0 is a big infinite jump, right? So, how much this is contributing depends on how important is it to any of these cuts, right? So, that's the kind of intuition that we want to capture. Another ways to think about this would be to say, how many paths are there from u to v? If there are more paths, right? So, in this particular case, if I take any edge u and v, if there are n nodes, if I fix uv, of course, u to v directly there is a path because this is a complete graph, but then I can go to any node and then go to u. I can go to any node and then go to u. I can go to any node and go to u, right? So, and there are so many, there are n minus 2 such paths already, but then I can take 2 node steps and also go to v, right? So, I will go from here to here to here and then to v. I can take 3 nodes, 3 jumps, right? So, there are multiple ways in which I can reach u to v. But even if you look at edge disjoint ways of going from u to v, I still have n such ways. I can directly go from u to v, or I can go to something else, right? So, u a1 v, u a2 v, uv directly, right? So, and u a n minus 2 v. There are some n minus 1 ways of going, edge disjoint ways of going from u to v, right? So, which means that this way of going from u to v is not going to affect so much, right? So, I can let go of these edges with, I do not really have to care about retaining any single edge in this graph, right? So, that is the intuition that we are trying to capture, and now we want to ask what function of the graph itself, given the graph, I need to associate some function, right. So, to get the probabilities of sampling an edge, which means that for this graph uv should have a high probability. So, whatever function that I am associating which takes an edge and gives a number out should give a higher number for this graph for uv, whereas for this graph any uv should have same number, but then a smaller number, right. So, and one can, I mean, there are other ways of thinking about this, and the standard way is to think of this like an electrical network, and then you are trying to ask what is called, I mean, in electrical terms they call it as the effective resistance across this, this edge uv. If you think of this as a electrical network, then what is the effective resistance in this path from u to v? And for our purposes, we can look at it as an effective resistance, or we can think of it as how important is uv to cuts, right. So, which is determined by how many edge disjoint paths are there from u to v. If there is only one, then that becomes a very important edge to be retained. So, that your Laplacian, because the Laplacian is a kind of an approximation of cuts. So, you have to retain all cuts reasonably well, so that to approximate the Laplacian. So, then if you look at the way PUV is defined, the way it is defined is as follows. So, it is defined as a quadratic form, and I will tell you what this is after I write this. So, this is the so this is proportional to this quantity that I have written down here, where EI is just a indicator vector, characteristic vector for the node I, where you set a 1 in the ith position and 0 elsewhere, right. So, what is this? So, this is just EU minus EV would then be 0 0 1 in the U position minus 1 in the V position, because there is a minus EV, right. So, that is EU minus EV, and this is also EU minus EV, and what we are saying is, this is just to say, we are measuring something between U and V, and the exact thing that we are measuring can be gotten by using what is called as the pseudo inverse of the Laplacian. So, this is sometimes called as the effective resistance of UV. So, again from if you think of this as an electrical network and then try to figure out using laws of physics, right. So, how much resistance would this edge u comma v have? Now the effective resistance would depend on the number of paths, right. So, if there are multiple paths, then you have other ways in which the current can flow. So, the effective resistance is going to go down across this, right. So, that is the intuition, and then I mean, instead of going and proving why this means that, which would take us into a long detour. So, I am going to just state the fact that you can compute the effective resistance as this particular quantity. So, again the intuition is, so now if you go back and calculate it for this kind of a node, what you will get is effective resistance for this edge would be something like 1, because there is only one path essentially, whereas for each of these you would get something like 1 by, if there are n1 nodes here, 1 to n1, and then if I have 1 to n2 nodes here, this will be something like 1 by n2, whereas in this case this would be something like 1 over n. So, what we are saying then is, if just to give some numbers, right. So, let us say there are 1000 nodes here, 1000 nodes here, and then this is something like a 2000 node graph. I mean, roughly the same number of nodes. This has 2000 nodes. This, I mean, in fact, exactly the same number of nodes, 2000 nodes in each of these graphs, whereas every edge, the chance that every edge appears in the sparse graph is very small, right. So, it is like 1 over 2000. Well, it is proportional to 1 over 2000. So, now if I kind of normalize this over all, so what to get the exact probabilities, I am going to normalize this, right. So, this is effective resistance gives me a number, and then the exact probability is just the effective resistance of this edge divided by the sum of the effective resistance of all the edges. That is how I would kind of compute a probability distribution over the effective over all the edges. So, that is going to be the same, right. So, that is because effective resistance is the same for all edges, because it is a symmetric complete graph, symmetric graph. So, this is going to be something like 1 by n choose 2, right. So, every edge is going to appear roughly with probability 1 by n choose 2, whereas here these edges are going to appear with probability 1 by n choose 2, I mean 1 by n1 proportional to 1 by n1, but this guy is much larger, right. So, this is like 1 by 1000, this is 1 by 1000, whereas this is 1, which is 1000 times more important to be present in the sparse graph than in the than any of these edges, right. So, these edges are much less important to preserve the Laplacian than this edge, right. So, the effective resistance succinctly captures that, right. So, and so we will use the effective resistance to sparsify our graph. So, what can we say if we do this, right. So, if I use this kind of a mechanism to do the sparsification, what we can effectively show, again we are not going to go into the probabilistic analysis, but we can show that with high probability what we want is true, which is F transpose LGF is at most F transpose LHF is at most 1 plus epsilon F transpose LGF, with where the important thing is that where PUV is proportional to effective resistance, sometimes called RF or effective of UV. If I do that, then okay, let me say if I choose PUV proportional to the effective resistance, then the key thing is that the size of F, right. So, the number of edges in F is order of V log V by epsilon squared, and this is the key thing. What we are saying is that the original graph could have been a very dense graph, could have had V squared edges, because if you have n nodes, n squared, the dense graph is going to have order of n squared edges, but then this is just going to have something like n log n edges, which is much smaller, right. So, of course, there is going to be a dependence on epsilon. If you want more and more stronger and stronger approximations, then you are going to have, you are going to have lesser and lesser sparser graphs. So, that is going to be a trade off always, but then in terms of asymptotics, so this is going to be something like n log n, right. So, order of n log n, if n is the number of data points, and this can be shown, right. So, and this is key, because now what we are saying is, if I just sample using effective resistance based sampling, then I can get a much sparser graph where the Laplacians are preserved. So, I can run my spectral clustering algorithm on this sparse graph, which needs eigenvector solvers, and there are fast solvers for eigenvectors for sparse graphs. I will make use of that. So, I can do clustering at scale much faster. Now, is this the best that one can do? Well, people have studied and come up with other methods which are faster than this, which are sparser than this, that you can get rid of the logarithm factor as well. So, there are more sophisticated methods by which you can say that you can get a sparse graph which is order of V, not order of V log V, but then that needs a completely different technique. But here simple random sampling already gets to something very close to optimal. That's the power of randomization. Now, one final point before we close spectral clustering at scale is, how do I compute these effective resistances, which seems to now depend on the pseudo inverse of the Laplacian. of the original graph, and the whole point was to kind of avoid doing this inverse business of the Laplacian, right. So, because we could not compute the original graph's eigenvectors in a computationally efficient way, so we wanted a sparse graph, but then to compute the probabilities for sampling, we need the pseudo inverse of the original graph itself, right. So, which means like a chicken and egg problem, right. So, so how can we avoid this? Again, one can do some interesting tricks, but let me show you one cool thing here. So, let us say for any edge, right. So, fix an edge I comma j, let us say. So, R effective of I comma j is just, let us call this Eij transpose L Eij. I mean, I am simplifying notation. By Eij I mean Ei minus Ej, by L I mean L inverse, by L inverse I mean Lg's inverse, right. So, the original graph pseudo inverse. Now, let us write this as follows. So, this is Eij transpose. The property of pseudo inverse is that, so I can do it as L inverse times L is just I. This is just the identity matrix. So, I can include that inside and then say this is something like this. So, this becomes Eij transpose L inverse. This L is just the Laplacian, which is a positive semi-definite matrix. It is a real symmetric matrix. So, it has an eigen decomposition, and let us call that eigen decomposition some U sigma U transpose L pseudo inverse Eij. Now, this is just my L, and I am going to rewrite this a little bit as Eij transpose L pseudo inverse U sigma half U transpose L pseudo inverse. I hope the pseudo inverse and transposes are looking different, because the notation wise they look similar. I hope that is clear. Now, this whole thing can be written as this times its own transpose, which is just the norm of Eij L pseudo inverse U sigma half squared. Now, essentially what then we are saying is that the effective resistance is some kind of a distance computation for every pair of data points. Of course, there is some matrix times the distance, the vector Eij, but then in that world, right. So, if I take a original matrix original vector Eij for every pair Eij and then transform it. So, maybe I will write it this way. So, I think that becomes even more explicit. Sigma half U transpose L pseudo inverse Eij, right. So, think of this as some matrix, and then I am multiplying it by Eij. Remember, Eij is just Ei minus Ej, some vector. So, this is in Rn, 1 minus 1 in the positions I and j, 0 everywhere. So, n dimensional vector, and now I am transforming it using some matrix, and now I am measuring the distance, right. So, it can be thought of as follows, right. So, this is like sigma half U transpose L Ei minus sigma half U transpose L pseudo inverse Ej squared, right. So, this is one vector, this is one vector, because Eij is just Ei minus Ej. So, essentially what I am computing when I am computing effective resistance, essentially I am computing the distance square between 2 points, and that is a great advantage for us, because in a different world what we are doing is doing distance computation, and if I want effective resistance for every pair of edges, every pair of nodes or every edge that is present in my graph, and because it is a dense graph, it is going to be order of n squared edges for which I need to compute effective resistance. Now, because this function effective resistance is just a distance function in some transformed space, and if I can kind of live with approximate effective resistances, is equivalent to saying I can live with approximate distances, and we know how to get approximate distances. And how do we do that? We can use the power of Johnson's Lindenstrass for that. So, there is a way to use Johnson's Lindenstrass. Of course, I need to talk about this. I mean, we need to worry about this transformation that also has L inverse. So, we cannot afford to compute the pseudo inverse, but then it suffices to say, you know, because of noticing that effective resistance is actually computing distances in a transformed space, there is a way, right. So, one can use JL to plus some tricks, right. So, and that tricks involves solving system of linear equations for the Laplacian fast in a quick way, which I am not going to talk about. One can use JL to get approximate effective resistances. Quickly. So basically what we are saying is we will preserve the effective resistance in a much smaller dimensional space, right. So, and then we can do this faster. So, once we do that faster, what we will eventually get, for example, I mean just to give some sense, for this maybe instead of 1 by n1, 1 by n2 and 1, which are perhaps the exact effective resistances, we might get maybe 0.95, maybe some 1 by n2 plus epsilon, maybe 1 by n1 minus epsilon or something of that sort. The probabilities are going to change a little bit, that is true, which means that, you know, I am going to have to pay that penalty in terms of how sparse the graph is going to be and so on, but roughly I am not going to lose so much because of the power of Johnson's Lindenstrass also, right. So, it kind of, you know, it gives a very tight bound, we already know that in preserving distances. So, in practice what you do is you compute effective resistances approximately and then use that to do sampling and get a sparse graph, and then, you know, run your sparse eigenvector solver for the Laplacian of the sparse graph and then do the clustering and use that as your clustering. On all these steps can be done really fast, right.